Hi friends, today we are starting a brand new series and it's on power machines and 5. My name is Tepo and please subscribe to my channel to make sure you keep on receiving videos like this. So our first lesson on power machines and 5 will be on thermodynamics of gases. So let's break thermodynamics into two. The word thermodynamics into two. First we have heat, then we have force. Thermo is heat, dynamics is force. So thermodynamics is the ability for this heat to do work. Since we know that force times distance is work done. And then there are a certain terms that we must first look at before we proceed with our lesson. We have first process, and then our second one, number 2, is cycle, number 3, energy, number 4 is the law of conservation of energy. So think of it as a company that produces acha. So every time they are buying mangoes and then producing acha. So it's acha, it's mango in, acha out. That's the definition of process. Process is being defined as an exercise that results in a change of substance. So first we had a mango going in, and then going out we have acha. Because of the high demand for acha, this process must be carried almost every day. So every day is the same thing. Mango in, acha out. Mango in, acha out. That is the process, that's the definition of our cycle. Cycle is being defined as a process that happens in terms of a repeated sequence. So for it to qualify to be a cycle, it must first be a process. Then we have energy. So with this one, energy will always be the ability to do work. There is no definition for N5 and a definition for N1. Energy, like we learned in grade 3, is the ability to do work. Never try to complicate life. The best definition for energy is the ability to do work. Then we have the law of conservation of energy. Think of it now as a room. We have a room, and then in this room we have a table that can take 8 people. So in this room, people are gambling. Each of these people, each one here have 1,000 rand. So these people are gambling, and each and every one of them have 1,000 rand, meaning that the total amount in this room is 8,000. So it doesn't matter who is winning or who is losing. The amount inside this room will always be 8,000. No matter who is losing, who is winning, this money cannot disappear. It can only change hands. And it is also true to say that inside here they cannot create money. That is our law of conservation of energy. It states that energy cannot be created. These people here, they cannot create their own money. Energy cannot be destroyed, and they cannot spend that money. Or they cannot eat it. Even if they eat it, they will poop it out. Energy can only be transferred from one form to another. Hence I'm saying that the money inside here, it can only change hands, but it cannot be destroyed, or they cannot create another money. So that are our terms explained in the best way possible. And then we have the gases part of the topic. So it is called thermodynamics of gases, and since we are now dealing with gases, it is important to know that we have two types of gases. We have what we call a real gas, and then we have what we call an ideal gas. We will not go deep to this way. The only things that you have to know about these two words is a real gas doesn't obey all conditions, doesn't obey gas laws under all conditions of temperature and pressure. And then ideal gas obeys the gas laws under all conditions of temperature and pressure. And then an example for real gas, it is steam. An example for ideal gas, it's your air. That's all what we are going to say about these two. And in this topic, we will be using ideal gases. So what are these gas laws that we are talking about? So we have two of them. First, we have your Boyle's law. Boyle's law. Erase everything. Boyle's law. Boyle's law states that the volume of a gas of a certain mass is inversely proportional to its pressure, provided that temperature remains the same. So this is a requirement. If temperature is not constant, this is not possible. And then let's try to present this in a useful format. So we have our V. We know that if you want to remove the proportionality sign, you must introduce a constant. In this case, we will be using C. It could be anything. A constant could be any letter. And then looking at this equation, we can express it in terms of y is equals to a divided by x. So we know that this is a hyperbola graph equation. Then let's make C the subject of the formula here. We have PV is equals to C. And then since we said this is a equation of a hyperbola, let's sketch the graph. This is called a PV diagram. And it is important to know how to draw this thing because it can be asked. We have our P here and then we have our V here. Let's take 2 points in the graph. We have our V, our P1 here, and then we have our P2 here. So now with P1 comes V1, and then with P2 comes V2. That is our graph. According to this law, we know that P1 V1 is equals to C. According to this law again, we also now know that P2 V2 is also equals to C. Therefore, P1 V1 is equals to P2 V2. So whenever you are told that temperature is constant, this is the formula to use. Now we have another gas law, the final one, the last one, called Charles's law. Charles's law. Now Charles's law states that the volume of a gas of a certain mass is directly proportional to its temperature, provided that our pressure remains the same. So P1 is equals to P2. This is a requirement. If this is not so, then this is not possible. Let's represent this formula in a useful manner. We have our V, removing a proportionality sign, we must introduce a constant. It's C times T. And then this formula can also be expressed in Y is equals to mx, which is our straight line graph equation. We make C the subject of the formula here. We get V divided by T is equals to C. And then, since we have the equation, then we sketch the graph. We said it's a straight line graph. This is our straight line graph. We have our T, and then we have our V. With V1 comes T1. With V2 comes T2. So according to this, we know that V1 divided by T1 is equals to C. According to this, we also know again that V2 is also V2T2 is also equals to C. Therefore, V2 divided by T2 is equals to V1 divided by T1. So whenever you are told that your temperature is constant, this is the formula to use. Whenever you are told that our pressure is constant, this is the formula to use. Then what if you are not told about any constant? So you are not told that T is constant or P is constant. Then in that case, you will use this formula. It says P1 V1 divided by T1 is equals to P2 V2 divided by T2. So you can use this formula if you have a statement that says nothing about any constant. So we have another formula that is like this. Erase everything except for this, of course. We have a formula that says MRT is equals to PV, with M being our mass and is measured in kgs, R being our gas constant, it's measured in kilojoules per kg Kelvin. And then we have our T. Now our T here, every time we are dealing with an ideal gas, we use our T in kelvins. So if you are given a T that is in degrees Celsius, means must be done to convert that temperature into Kelvin using this formula. So to the number that is given in degrees Celsius, you just add 273 and then you get your Kelvin. That way you can proceed with your calculations. Never, ever, and ever again put a number that is in degrees Celsius here, because even before you even start with your calculation, that whole thing will be wrong by then. So our P is in, that's pressure, and it's in kilopascals. And then we have our V, that is volume, it's in cubic meters. Yeah, that's everything. Those are our SI units for this equation, and it's called an ideal gas equation. Yeah, something like that. And then we have now specific heat capacity. Specific heat capacity. Specific heat capacity. Specific heat capacity is the amount of heat required to raise 1 unit mass, 1 kg of gas by 1 degrees Celsius. That's our specific heat capacity. I'm sure you do know this. So suppose we have a piston. This is our piston, the most beautiful piston in the planet. Yeah. And then we have gas here. This gas is now heated using an external source. And then now we fix the piston in a way that we do not allow the volume to increase. So V1 will be equals to V2. Now the specific heat capacity in this manner, when you write it, you will have to specify that this specific heat capacity was taken under a condition of constant volume. So if you write it, you just write CV. It's a specific heat capacity under constant volume. It won't be the same as a specific heat capacity of the same gas, same amount that is open to the atmosphere. Therefore, you will have to specify. Take another instance where now you allow this piston to move, but you fix the pressure. You carry this process in such a way that pressure remains constant. Now, you will have again to specify when you are writing that it's a specific heat capacity that was taken under the conditions of constant pressure. So every time specify that this specific was taken under this condition. And then yeah, let's take now, we have a piston. That's our cylinder, that's our piston, the most beautiful piston in the world. And then that's our piston. And then we have gas here. This gas now is heated, and this piston moves this tense L. Now we know that there will be work done in the piston by the gas. So if we want to find the work done now, we know that work done is equals to force times distance. That's distance is our Then according from this force times F, from this equation, we know that F is equals to PA. And then we can come and substitute our F here, seeing that is PA. And then our L is the distance moved by the piston, that's L, times L. L, not 4, L. Looking at these two, we know that area times volume is equals to, area times length is equals to volume. Now we can substitute these two by V. But this V that we are looking for here is the change in volume in this cylinder. So we will say P, that's our work done. We'll say it's equals to P, this P, and our change in volume, which is V2 minus V1. So this is the formula we use to calculate work done. Now, the amount of work done by the gas in expanding will depend on the method by which expansion was performed. So we have 5 in this syllabus, or in this subject. We will be dealing with 5 methods by which expansion can be performed, and we will be looking at those methods now. We have 5. First, method. Straight line. Yeah, okay. We have first our constant volume, V1 is equals to V2. Now in our constant volume, as we have seen, our work done is P V2 minus V1, and in our constant volume our pressure are the same, meaning we will have P times 0. Now we know that each and every number times by 0 is equals to 0, meaning that in constant volume we do not have any work done. And then our Q, that is heat added or heat rejected, will be calculated using this formula. M is equals to CV change in T, T1 minus T2 minus T1. And then our change in internal energy. Change in internal energy will be given by this formula, which is the same as Qm times Cv is equals to change in temperature times C2 minus C1. That's our change in internal energy. So we are done with the first method. We have another method, and it's constant pressure. So in our constant pressure, because there will be change in volume, there will be work done. So we said work done is given by P V2 minus V1. And then our heat added or heat rejected now will be given by this formula, M times Cp times change in temperature. And then we have our internal energy. Internal energy, change in internal energy will be given by the same formula as well. T2 minus T1. That is our method number 2. And then we have our method number 3, which is T1, constant temperature. And it's performed using this law. here, if we want to calculate our work done, we no longer use this formula. Now we use another formula that says P1 V1 ln V2 divided by V1. In other question papers, you might find that they wrote it as P1 V1 log of base E V2 divided by V1. So don't be confused, because ln is equals to log base E. So these are basically the same. Don't be confused. And then another formula that you can use here is MRT1 ln P1 divided by P2. And then in this case again, we know that MRT is equals to PV. These are the same. And then we know that V2 is equals to V2 V1 is equals to P1 divided by P2. These are also the same, so don't be confused. It's from the formula that we learned that says P1 V1 is equals to P2 V2. So don't be confused. You can use any of these two as long as it complies with the information given to you. So our change in Q will be given by work done plus change in internal energy. So our change in internal energy, since it is as a result of temperature or temperature increase or temperature decrease, in this case it will be 0, because our temperature is constant. So changing in internal energy is 0. Then we have our fourth method, and it is the polytropic method. And then it's performed using this law: PV exponent n is equals to C, with n being the index of polytropic. Then now to calculate our work done in this case, we will use P1V1 minus P2V2 divided by n minus 1. Or we can use MR in bracket T1 minus T2 divided by n minus 1, depending on the information that you have. Then our heat added, heat rejected will also be given by work done plus the change in internal energy. Then here the change in internal energy will be given by M times CV times change in T, T2 minus T1. So in this one we have additional formulas. First we have a formula that says PV exponent n is equals to P1 V1 is equals to P2 V2 exponent n. And then we have another formula that says T2 divided by T1 is equals to P2 divided by P1 exponent n minus 1 divided by n. And then it's equals to V1 V divided by V2 all raised to n minus 1. then we have our last but not least method. It's called adiabatic method, and it's performed using this law PVR is equals to 2. Then our work done can be found using this formula P1 V1 minus P2 V2 all divided by R minus 1. Here we said in polytropic we said that N was the index or is the index of polytropic, and then here we now have R. R is the index of adiabatic. And then another formula for us that we can use here is MR T in bracket T1 minus T2 divided by R minus 1. So in adiabatic process there is no heat rejected or heat added, so Q is equals to 0. Then internal energy, same formula again, M times CV times change in T, T2 minus T1. In this one also we have additional formulas. We have P V exponent R, P1 V1 is equals to P2 V2 exponent R. And then we have another that says T2 divided by T1 is equals to P2 divided by P1 exponent N minus 1 divided by, sorry, it's R, not N. R minus 1 divided by R is equals to V1 divided by V2 exponent R minus 1. So this is the whole summary of our processes that we will be using a lot in this topic. So make sure you have this table every time by your side when you are practicing, because it is very important that you are able to locate the correct formula that you are looking for. Using this will give you an advantage when you are now using a formula sheet, because if you know exactly which formula you are looking for, it will be easy for you to find it in the formula sheet. In the formula sheet, they are not given in a formula in a table form, they are given in a list form. But if you know what you are looking for, it will be easy for you. So my advice, have this table, copy it down and have it by your side. Every time you are practicing, use this table. And then eventually, when time goes, you will master these equations and they will be in your head. So there will be no need for you to go and refer to this table over and over again. So now we have the last thing on this topic. I'll erase this. Hopefully you have copied it down. We have what we call entropy. Entropy. So entropy is the transformation when we are expanding a gas. That transformation from its initial stage to its final stage, that's entropy. We do not go deep to this with in this subject. The only thing that is important is the equations. So we have two equations of entropy. Entropy is represented by S, and then we will be calculating change in entropy, which is S2 minus S1 is equals to M. These are our two equations. Only have two of them, and then we are done with entropy. V2 divided by V1 plus CV ln P2 divided by P1.
second formula is change in entropy is equals to M in bracket Cp ln T2 divided by T1 plus, sorry, it's minus R ln P2 divided by P1. So that is basically the end of our lesson. I didn't want to add exercise in this video because I think it will be too long and I don't think it will be necessary, enjoyable if it is too long. So I will make another video showing how to apply the information that we have just learned today. We will do exercises in the next video. In the meantime, try to do the exercises in your textbook. I will do another video showing how to apply this information. Hopefully this video will help you understand what is thermodynamics of gases. I wish you good luck in your studies. Don't forget to subscribe to my channel. Comment on this video. Tell me what you think about today's channel, about today's lesson. Tell me what you think about this channel in general. Don't forget to subscribe, share this video with your friends. From me to you, I will see you in the next video.